All right, welcome back. In this lecture, we will look at inference rules. Here are the lesson objectives. Now, if we recall, a logical consequence is defined as when you have a set of assumptions, A through N, which is maybe your existing knowledge of the world, we say that B is a logical consequence if every time A1 through AN are true, then formula B is also true. Now, if you do this evaluation using truth tables, then you're quickly going to run into trouble when you have more and more propositional variables. You will run into an exponentially large truth table. So this is not good. We want to look at ways to avoid this. So we have this idea of a proof rule or inference rule, where we maybe have some information that we know that, hey, given a certain propositions that are true, something else will also be true. And we can think of a very easy example of this would be that if we have, let's say, A is true and B is true, well, we can conclude A and B is also true. This follows right from the definition of a conjunction. And so we can write a bunch of rules like that to help us with the inference process. Now, we could create a set of these rules, and they are called logically sound if they're correct. So the one I just drew on the slide for conjunction is an example of a logically sound proof rule because it follows right from the definition of conjunction. Anything that we conclude resulting from that rule is going to be correct, and we can evaluate that and prove that it's correct based on the truth tables. Now, we say something is complete when we can be sure we can derive every possible outcome. Now, if I gave you only a logical or only a proof rule for conjunction, it won't allow you to do any additional reasoning if negation or disjunction are present. But for everything where that focuses on that use of conjunction, it'll still give you the right answer. So a set of rules is sound if for each rule the conclusion follows the premise and is done correctly. And again, we say it's complete if all of the logical consequences can be derived from one or more of the proof rules, and when we say more than one proof rule, we could chain them together and apply them iteratively. So we'll wrap up the lecture by talking about one of the most important proof rules that's widely known, and that's modus ponens. And that is if we have P and also this assumption P then Q, then we can derive Q. And this, just looking at it, makes a lot of sense. It follows directly from the intuition of an implication, and it is correct based on the truth table definition. So example here of this being applied in a situation with propositional variables, we have raining, and then if raining, then wet grass, we can conclude wet grass. Now the following is not modus ponens, and we have A equals 2 and A plus B equals 5. Now these are two statements, but we can't, they are not being combined together using any kind of connector. So we have three statements that are potentially all different. A equals 2, A plus B equals 5, and B equals 3. Seeing this and thinking it's right, we only believe that because of our underlying knowledge of how arithmetic works. But from a purely logical perspective, this is not a valid proof rule. So with this in mind, let's revisit this concept of the logical agent. So the logical agent has a knowledge base and an inference procedure, and often what we see in propositional logic is the knowledge base is a set of propositional formulas, our assumptions about the world, where the inference procedure we can view as the set of rules that is used, or inference rules, used for drawing conclusions about those propositional formulas. So thank you for tuning in, and please check back for more content.